Well, hope everyone's doing well. Uh, Today we're gonna talk about Dask, and I'm hoping to also kind of open up the floor and talk a little bit more about kind of parallel computing in general, and you know, methods for doing that, how it might fit your different research needs or different computational needs, um, and then like sort of the other resources we have. Um, at UVM to sort of parallelize things. Um, so with that, let's jump into the tutorial. Did people get a chance to like breeze over the tutorial? I didn't expect everyone to like fully read it because it's kind of long and is more of a tutorial than an article. So no worries if you didn't. But is anyone here familiar with Dask? I'm just curious, like if you want to raise your hand or virtual hand, you are. No. Cool. So this will be good then. How about like parallel computing? Has anyone done any sort of like parallelization before? Maybe not with Dask, like with back a little bit. Cool. Okay, cool. I think this
These
will
are like
be
all things I've heard of, but like don't have any clue how to implement or anything.
okay, cool. That's awesome. Thanks, Ryan. Yeah, no, this is good then, because it's one of those, I feel like concepts that's kind of like to non-computer science folks, it's I feel like myself included, honestly, because my computer science background was like kind of limited, but like it's kind of has that kind of like aura of like mystique or like it seems a bit esoteric, but because there's a lot of jargon involved, I feel like. But once you get familiar with some core concepts, I feel like it starts to make a lot more sense. Um, so anyway, let me share my screen here, and we can kind of talk through that Dask tutorial because that's a good place to start, I think. Okay. So this course I think was from UCSB. Um, there's a lot of desk tours out there. There's a lot of documentation. I like this one because kind of simple. It starts with like pandas data frames, which we all love, easy to work with. And then it gets into kind of demonstrates how you can use X-ray as well, which is good for like um, geospatial data, as we've also talked about before. Um, so cool. I'll put a sort of paraphrase these little sections here. Um, so yeah, what is Dask? Dask is a Python library for parallelization. Um, and maybe start what parallelization is. I think it's best to kind of start with an example. Say you have a really large data frame, right? And like a CSV with like thousands of lines, and you want to, read it into a Jupyter notebook, do some EDA, or some analysis onto it. Um, well, if it's really big, it might take up more memory than you have available. Or it might like really slow down. It might be really slow to like run these sorts of analyses, or worst case end up crashing um, the Jupyter server you're currently running. Um, so what you can do with Dask, and this is sort of the parallelization process in general, is you can chunk up this data frame and set up what's known as a cluster. And what this cluster does is kind of it's a way what Dask does, it provides like the sort of scheduling of your different tasks. So if you're reading in this large file, instead of trying to read it all at once, what Dask will do is say, okay, let's read this in chunks and then distribute these chunks to um, different workers. I think it's a jargon they use. Um, and a worker is basically there's two different types of workers that you'll probably hear about, and that's threads and processes. and we can dive a little bit more into the difference between the two. But basically, note that the workers are what are doing the heavy lifting. They're what's doing the computing with your code or with your data. Oh yeah, and so we were talking about cluster here. So actually, let's go down to this diagram. So you can think of your workers as your threads, cores. There's a lot of kind of different terms I've heard to describe different types of workers. And if anyone has any insight or thinks I'm saying anything wrong, please jump in. But what Dask will do is, so it sets up your cluster, which is basically this system in this diagram here, where you will write code, pandas commands, for example, and send those commands to the client. And like say you want to take an average across your whole data frame. Then you'll tell that to the client through your direct coding. The client will tell that to the scheduler, and the scheduler is basically this interface that mediates the chunking and the distribution, basically. So the client, you tell the client what you want to do, client tells that to the scheduler, and the scheduler is like, okay, it's monitoring the resources you have available on your computer, monitoring processes, and distributes them to the workers as necessary to get that done efficiently, get the task done efficiently. Does that make sense? I feel like I just threw a lot of jargon at you guys. But does that make sense? Cool. Okay, then I'll keep going. Keep going, spinning here. And yeah, so this is a bit of an interactive tutorial, so maybe I'll switch back and forth with my code here. So this is, I think, from a class. So basically they had somebody set up a cluster. And there's a couple parameters here. N workers, that's like gonna depend on the size of your machine when you're running on. Like your laptop, for instance, might have, a different number of workers. The more workers, the more power you'll have. This processes argument or memory limit, auto, seems like a good default to stick with. Processes equals true or false. That gets into this difference between processes and processes or threads, which are the two main types of workers. And was it actually maybe, oh yeah, this is good to show. I think it was this tab, or no, that's a Medium article. Maybe it was this one that showed the differences. Yeah, okay. So this is getting into a little bit of the difference between threads and processes. So in my understanding from what I've done with parallelization, whether you want to use threads or processes kind of depends on what your task is. So if your task is computational, like crunching a lot of numbers, doing a lot of math, like calculating some statistics over your data, that's going to be very CPU heavy, and you're going to want to use processes for that. If your task is what's known as I/O bound or input-output bound, those are things like reading in. Those are things that are typically like, memory bound, like reading in a large file or downloading a large file from the internet. So sort of like things that read or write large amounts of information to disk. Those things are going to be better suited with threads for workers as opposed to processes. And you can read more about like the nuances or the why, like and that kind of gets more into like computer hardware and engineering. That's even beyond my scope, but like that's kind of like the path you'd go down if you want to learn more about that. And this kind of this Dask documentation kind of shows you what is kind of going on under the hood here. This is a Python package. I believe it's built in actually. Concurrent futures, thread pool executor. You can use, so this would be like setting up if you want to use multiple threads, you could do this manually yourself without Dask. You could do like with concurrent.futures.thread pool executor and then say how many threads you want. That's maybe like, a little simpler if there's just like one or two things you want to do with multiple threads. Then you can use like a context manager and circumvent Dask and just use this thread pool executor, and similar thing with process. We have the concurrent futures process pool executor. Lightweight, doesn't require the setup that Dask does. So pros and cons, like lightweight, easier setup. You have to know a little bit more about what exactly you're doing as opposed to Dask, which requires a little more setup, but there's a little more control there with that client scheduler model where you interact with the client. The client kind of like is the talks to the scheduler and such scheduler. Whereas I would say if you're directly interfacing with these thread pool executors, you're kind of the scheduler. So you're the one telling the workers what to do, which again gives you more control, but easier to mess up. Pause again in case anyone has more questions. You can also raise your hand or anything like that if you want to stop me talking. And I'll look out for that, or in the chat. That's dashboard. Oh yeah. So let's kind of go. I really didn't spend too much time in this tutorial, just kind of like copy and pasted the notebooks or the cells from that tutorial into a Jupyter notebook. And for those curious, I'm actually running, so this Jupyter notebook running on the VAC. And we do have some, actually, yeah, I do like to use the VAC a lot just because in my own work, I've been doing like a lot of my data is stored on the VAC. And, I was running a lot of experiments, submitting a lot of jobs to the VAC, so it was just more convenient for me to have VS Code on it. But you could also do this on the test bed, the VN Cairo test bed.
No, you mind up in the text size or zoom in a little?
Yes, thank you. Yeah, this is a big screen. Zoom in here.
Perfect.
Maybe that's probably good. Is that good?
Yep.
Great. Okay. So here we're setting up a local cluster, which again is like sort of setting up that trifecta, that client, or setting up that scheduler worker. And then when you set up, that creates like an address. That cluster has an address. So the cluster is like that cluster of workers. When you set that up, you can pull the address from the cluster attribute. And then you can import client, and then you can create a client based on that address. But you see that address is sort of looks like an IP address. You can actually, Dask is nice because it has like a dashboard, like a web dashboard. You can't really click on this address, but if you do some port forwarding, if you forward the local host, this is your local port 8787. And then once I have that forwarded, I believe it was, I think it's open a browser. There we go. And you can see you get this really cool Dask dashboard, which is empty right now because I haven't done anything. But you get all this information about CPU utilization, your processing, data transfer, byte store per worker. So you see there's like 4 workers here. And if you go back, that's because I asked for 4 workers. I didn't want to ask for too many because the VAC login node does not have that many, and they don't like it when you try to parallelize stuff on their login node. But cool little interactive dashboard. Kind of see the status of different workers, different tasks. Not much going on right now because I haven't done anything, but we'll see if we can try to get it to do stuff. Then the tutorial went through some sample data. So a few more imports there. This was, I believe, Arctic soil moisture data as a CSV. So from this URL, so I'm just going to pull it from this URL and try to read it with. Notice this is not Pandas, but now I'm using this Dask data frame pack library. So this reading in the data frame using the Dask data frame library is going to read it in chunks. And basically we are saying the block size here, or the size of each chunk essentially is going to be 20 megabytes or megabits. And the tutorial had some more information about choosing your chunk size. Oh, and this is a nice visual representation when we're talking about these chunks, right? So when you have a Dask data frame, it's built of smaller chunks of Pandas data frames, often called a partition. Let me zoom in here too, just so it's bigger. So this is a visual reference. Dask data frame is made up of different partitions, chunks of which individually each is a Pandas data frame. So reading in this data, we did that in the notebook here. This tutorial, they've figured stuff out for us with the block size and everything. That'll really depend on if you're doing this with your own data. The block size is going to depend on the size of the file you're trying to load in and how much RAM you have on whatever machine or cluster you're working on. So yeah, let's go back, take a look at the data frame we've read in. So you can see we don't get any data, right? We get different information. We can see columns that are in our data frame. We can see the data types. We see the number of partitions we created. So we can see the kind of overall structure of that Dask data frame. But what Dask has done is basically it hasn't loaded in all the data itself. That's part of its, kind of lazy computations, trying to save memory space. It's just sort of loaded this structure. And then if we call the data frame, if we call the head, then that'll actually, send some information to the workers and load, in this case, the first 3 rows of data. So now calling the head, now we actually executed some computations here. We loaded in the first 3 rows of our data. And now let's go back and maybe talk about lazy computations. So with lazy computations, basically, when you run a command, like say you want to on the yearly averages or whatever, what have you, for your Pandas data frame. A lot of these methods are very similar, like because remember, technically DF is a Dask data frame, not a Pandas data frame. But these probably look familiar to those of you who have worked with Pandas. It's the exact same code, exact same syntax, but they are different methods. So a lot of times the methods you use on a Pandas data frame are basically the exact same that you use with Dask, but not always. So always check the documentation first before you do anything. And that's because, again, it's doing these, when you're using Dask, you're doing these lazy computations. which means the client tells the scheduler, okay, here's all the computations we want to do, but you're not going to explicitly execute and get results until you run this compute command. And then once you run compute, then the scheduler's like, all right, workers, get to work, allocating memory and resources to run those tasks in parallel. And you can see that's the big benefit of Dask. That's how most of these, this method of kind of executing code is called lazy evaluation. And that's how most of these workloads work. As opposed to like Panda, or, the original Pandas, which uses what they call eager evaluation, which as soon as you call, group by mean, it's going to execute that right away. It's not going to wait for you to call compute, right? It just does it straight away. So let's try to do that, and then maybe we can take a look at the dashboard. Okay, that's unexpected. Numeric only false. Let me see if I can just do something else. Yeah. Maybe if we did median. Let's try that. Not averages anymore. Nope. Okay, this is weird. This might have to do with some imports or like incompatibilities. The DF head works. What else could we do? I'm trying to think of just doing like some kind of minimal. Okay, well, we can get the min. Not gonna be averages. Change that to min. Not really a. I guess it's kind of a computation. Okay, and now let's see how that affects our dashboard. Oh, gotta run compute. Oh, this is the wrong one. This is the one, right? Status. Yep, so still blank. Now if we write, I think it should be compute minimum, right? Or minimum dot compute. Okay. All right, now we're getting our calculations back, which I guess is going to be the minimum row for each year. For 5 year. Interesting. But anyway, wait, the calculation itself doesn't really matter, but just for demonstration purposes, we'll steal it. And now let's see if I have to reload this, I think. Let's see. It just showed up in tasks. That's strange. Maybe because it was a numerical calculation. Averages didn't work. Oh well, I don't want to spend too much time on this tutorial because I want to open the floor to like a broader discussion. But this, ideally, you would be when Dask is running, you'll be able to run your computations. You won't see any results until you run compute, and then I know I can at least show you what it looks like. The dashboard. Yeah, so this is kind of like kind of example of, I can't make that bigger. When you're executing stuff in Dask, the dashboard kind of looks fancy. Honestly, you probably don't really need to use this, but you can kind of see it's running all your tasks here. It's kind of showing the different workers for the task stream. This is the bytes, the memory stored by each worker. You can see the overall memory is increasing but it's split up by each of these workers. And CPU utilization for each of them is below max, which is what you want. You want to max it out. And let's go back to our tutorial. What time are we at? 10:30. Okay. So to quickly kind of go through the rest of this, there are other data structures in Dask that parallel to sort of those eager computation data structures. It's like much like a NumPy array, you have a Dask array, which is each made up of chunks of NumPy arrays. You use Dask with X array. I won't go this far, like demonstrating this in the notebook, because it is end up being kind of quite a long tutorial. But hopefully this demonstrates at least, or at least gives you guys a taste of that, like Dask can be used. Basically, whatever kind of computations you're using, calculations you're doing, most of the time you can parallelize it with Dask. But of course, there are questions of like, when do you parallelize? When should you parallelize? And then how, in terms of like, depends on the resources you have available. Like whether you're doing it on your local laptop, for example, or the test bed, or the VAC, because each of those are three different machines, and they're going to have three different, different amounts of resources for you to utilize. Different number of threads, different number of workers, different amounts of RAM, etc. So that's kind of a general overview of parallelization. Again, a lot of times it does it's hard to say like, oh, always. It's possible to say like, oh, always use this number of workers, always use, threads, or always use processes, because again, it depends on your task. But hopefully that gives you a general overview of like how parallelization works and sort of the framework that Dask has adopted for executing that in Python. And yeah, so we're about halfway through. So I want to stop sharing and sort of open up the seminar for conversation. So I know it seems like a lot of us haven't really done much parallelization. But it's maybe something people are interested in. So I thought maybe we can share like first off, if you have any questions about parallelization, we can talk about that, and I'll do my best to answer it. I'm not an expert. I have done parallelization before, but I would not call myself an expert. But yeah, I guess I'll start by sharing like what I've used parallelization for is some of our data modules, acquisition modules. When we're downloading, say, national water model data, for example, which is like the whole CONUS for one time slice. Those are huge files. And especially, so it's annoying because if you want to grab like a 10-day forecast, well, you can't just grab it. You can't just download the way the files are structured, right? It's like each time slice, each hourly, forecast or interval is for the whole CONUS. So that's a huge file. If you want to get the 10 days, that's like 240 files, right? Of all of CONUS. So the only way to really get, even if you're interested in one reach, so you still have to download all those. So what we've done in our code is use that concurrent futures thread pool executor to speed up downloads. Instead of doing download one by one, we can use we use up to 8 threads, which is generally, well, by default, we use like half of whatever threads are available on a machine, which is usually around 8. And so then we can download basically 8 at a time. So it's 8 times faster, which is a big help. And you can do the same thing when you're reading in data. So that's one way I've used parallelization. Don't use Dask for that. Because I'm not working with huge, because that's more of a, like I said, IO bound task, reading in files or downloading files. So it's kind of a simple, oh, we just want to speed up the download of these files. Let's use parallelization to use 8 threads instead of 1 and do it one by one. Instead, use 8, do it 8 times faster.
I have a question. Have you done anything across more than one node with this? And I'm not quite sure how that like interfaces with Slurm to reserve nodes. And so you said you use half the threads on a machine. So if you go to a node, you've got just so many cores to work with. So there's so many threads you could launch independently. Have you done anything with multiple nodes? Or is that outside of Dask?
No, I think on the so like my understanding is like when it depends, like say like if I ran say that download script on the login node, like from a notebook, or if I submitted it via Slurm on the back. If I submitted via Slurm, then each job would get its own node. And so in each node, I'd be using 8 threads. So you could potentially, if you set your code up right, you could do that download really fast. And
I didn't know if Dask was in between you and the nodes, or is it on each node you run a Dask?
I think it is, I think on each node, if you use this, I'll share the local cluster.
I saw, yeah, I guess I'd have to go and look some more. I saw some pointers. It sounds like there's something there. I just didn't know if anybody done anything with multi-node reservations with Dask.
Yeah, I think you can set up, that's a local cluster. I think there are other types of clusters you can set up where you can have multiple nodes basically. But I haven't done that. I don't know if that's an interesting question for the back though. Like if they would let
I do see that. underneath that docs-dask.org, there is a Dask distributed cluster. It says you can run Dask on a distributed cluster, variety of ways. There's configuration files.
That sounds like that would be the method.
Yeah, sounds like there's potential there. I'd have to go poke around and see if there was anything, because sometimes we need more than a node's worth of work done, or the work we want done on each node is hefty enough that we can't do more than one of them on a node. Like the job we're running is a multi-thread in itself.
Yeah.
That's what we ended up using.
Yeah, that seems.
We've used the Pegasus framework. It's not so much for parallelization of one routine threads in a particular calculation. It's for launching a pile of jobs, a pile of separate scripts to run. I mean, it's kind of a different problem they're solving if you're trying to do a very fast single calculation on a data set versus trying to run 500 scenarios, which needs to stand kind of alone. Yeah.
Right, where each job is like independent, or
right. They just need to get back together again at the end, or even if you sync by file, not by it's like when a file gets output, you say, okay, the next thing can happen because that file got output, or when all of the children finish their work, the next generation can pick up and do the next thing. So, yeah. Another tool in the toolbox, not a problem, not a bad thing to have. I'll have to look into it. Haven't done a thing with it. I didn't know what Dask was. Couldn't even spell it 2 weeks ago.
I have a few comments, Noah.
Yeah.
One of the things I always struggle with is like, at what point is it worth the additional effort of transferring over to Dask versus just waiting like a day for everything to run on the test bed or something like that? And
Mm.
I don't know, there's maybe not like a simple answer to that, but like, I don't know, if you're thinking about when do you start switching to parallelization, what do you think about?
Yeah, well, that's a great question. And the first thing that comes to mind is reproducibility. Like, if I'm running a script or something that's going to take a day, and I know with 100% certainty that it's going to do exactly what I want without an error, then like by all means I'll do it. But like that's almost never the case. You know, you always run into like bugs or sometimes most of the time it doesn't work the first time as you expect. Um, and so a lot of times, you know, it's a pain in the butt to like spend a long time on something and then you run it and then like, okay, it's out of my hands, it's running. But then you check a day later and it crashed in the middle of the night or it didn't do exactly what you wanted to do. And then you're like, okay, well now I have to like figure out this bug, fix it, and then run it and wait again. So that comes down basically to yeah, reproducibility and like speed because it is like definitely more work up front to set up to make it to parallelize the script you're running. Um, more work and like definitely learning involved, but like it can it can really save you time down the line if it's something you're gonna be working on for
Yeah.
more than like a week or something, you know, and
I
you're gonna have to
I
run it
haven't
again in the
done
future.
this. Haven't done this for Dask, but I've certainly done it for other things. It ends up being often an issue of scaling, or like if
Yeah.
I need to do something 5 times, like I can do it 5 times and take the long pull and let it go. If I need to do it 500 times, if I need to run it every day, in the year, you wanna make it efficient. You want to get it done and get it over with. So that's when I end up putting time in to parallelize things or to automate it with batch it.
Yeah,
I
thanks.
I kind
All
of
those, oh, sorry, Shari.
go ahead, Ryan.
Oh, I was just gonna say all those nightmare scenarios you described have happened to me. So
Yeah, I kind of end up. I didn't use Dask, but I did use concurrent features, threaded, and process pool executor whenever I was working with MRMS. Uh, so specifically for downloading files from a specific URL and specifically downloading, I guess, spatial data for CONUS is a large task, and you can easily run into memory caps, which can make your code crash and whatnot. So I did end up using threaded pool executor whenever I was downloading those grib2.gz files. Again, repetitive task, very large amount of data being downloaded. So having those multiple threads can really help out with those network requests because those are input-output bound tasks. So it definitely sped that process up from, I think, 7 days to maybe 3 days. Uh, Again, the number of maximum workers it's correlated with the number of CPU cores that you have access to. So if you do have multiple devices or you have enough cores, then it can be even faster. As far as process pool executor, that was more so for CPU bound calculations like neural network weights or extremely deep learning models. Have kind of messed around with that, not as extensively as threaded pool executor, but there's definitely benefits in terms of processing speed and, as Scott and Noel mentioned, code organizability, reproducibility, all of that stuff. But yeah, some of these things are just you're 5 days into the download and something crashes because of a memory timeout or usage timeout. So it could get annoying. And I've also, I think I posted a link in the chat. I've also used the TensorFlow library package called Mirrored Strategy to use multiple GPUs on the VAC. I'm pretty sure you could use the same thing for multiple nodes as well, Scott. I'm not sure how efficient it would be because I think when I was trying to run my deep learning models on the VAC and I talked to Pat about this, he was saying that it is possible to use multiple nodes and multiple GPUs in those nodes with this merge strategy, but it would really be, it wouldn't be as efficient because then whenever you're recombining the input outputs or calculations from different nodes, that process would take time regardless. So all of the upfront speed that you do get from using multiple nodes won't be worth it at the end because that recombining of results will take just as long. So that's why I kind of just stuck with one nodes and 2 GPUs, I think, per node is what the VAC offers. But using mirror strategy definitely helped.
Interesting. So you were saying on the VAC, it turned out to be not worth the effort to try to use multiple GPUs across other nodes because sort of the coalescing of that data back that'd be like the bottleneck, and so it wouldn't be much faster overall.
Essentially, yeah, the communication between the multiple nodes would be the bottleneck, where you really couldn't speed up that particular process itself. So, I think Pat has suggested it wouldn't be worth trying to use multiple nodes, period, because at that point I was trying to consider how much faster can I make these models run, because I was trying to run a lot of models at that time, and with neural networks they can get pretty extensive pretty quickly. So I just stuck with one nodes with 2 GPUs, and that ended up working pretty well. But I do have to admit I didn't try the case for multiple nodes. Obviously, with the increased code complexity, and ever since the VAC had their little patch or update this past summer, even the code that used to run flawlessly 2 months ago is now not running at all. So I'm not sure. The more that code complexity increases, I'd imagine with these tiny updates here and there, with CUDA libraries or CUDA versions changing and all of these library mismatches coming through, that it could be a pain in the butt in the long run.
Scott, you're muted.
I'm muted. I say making a
Oh,
complex infrastructure is a mixed blessing. For that very reason, it can be fragile, or especially if you're not in charge of doing your own updates. Somebody's going to say, "Hey, I'm going to change this thing tonight." Oh, that's great. I needed to run 500 jobs this weekend, and you're going to bring down this required service.
I've sat with the VAC folks a couple of times since that update, and they say that they haven't changed anything. All the CUDA versions are intact. The UDNN versions are intact, but I'm telling you, it's the same code. It just won't run anymore. It says it can't find the necessary packages anymore. It's either their module loading is not working the same way, or I don't know. But to your point, complexities are could be a double-edged sword.
Yeah,
it's great for a while, but yeah, it could come to bite you in the butt real fast.
Cutting edge, sometimes you get cut.
Yeah.
No, thanks for this. I guess what comes to mind first for me is like a really common task that I need to do is like calculate some like watershed area average, like essentially a zonal kind of statistics. So this sounds to me like if I need to do that over a ton of watersheds, that help. But that like would you? I guess I'm trying to think of like you need to have your data in a way that is like sort of like easily broken apart or indexed like by watershed, right? So like if you wanted to do that,
With
would
Dask, I
that
would say
like
yes. Yeah.
say you had like a raster, you would yeah. Would that raster data like need to be in a certain format so it like knows kind of where to get it, or is that kind of like built into Dask? I
I
don't know if that
think
question made sense.
I think I get what you're, yeah, I think I get what you're asking. So like, yeah, because like, so like if you had a raster, I don't think you would need to any special format, but say like your raster file, if you somehow were able to compile all those different zones or different watersheds into one raster, so it was like this massive raster, um, then I think Dask would be, you could use, I don't think you'd have to do any special reading with Dask to read that in. You just tell it the chunk size, basically, that you want to read it at a time. However, I haven't worked much with rasters, but if you would, I wouldn't go through the trouble to compile a large raster that big, right? Like if your rasters are already digestible without having to use Dask, then you can do a different method of parallelization with something like the VAC. Like for example, you could write your script that you would want to run on each watershed. And like for each watershed, we'll do all this stuff. And instead of putting that in a for loop, for example, you could parallelize that on a something like the VAC, where you can run all those instead of a for each loop kind of thing where it goes through each one individually. You just say, because they're all independent calculations, you can say, oh, just do it all at once with the VAC, and then the VAC will distribute each of those jobs to different nodes, and does it all in parallel instead of doing it all at once. So that's a great question, because that I think gets to this question of like, it depends on what your data looks like in the first place, right? Because it doesn't make sense to like compile a giant file for Dask or break up a giant file to use something like a parallel computing system like the VAC, right? These things are designed to fit your data. So like whatever way your data already is, there are methods for doing it. So I've sort of, I kind of take like a data first, think of it with like a data first approach, and then what's the best method for your data, if that makes sense.
Yeah, yeah.
And I saw you in the chat, Scott, you mentioned SnakeMate for Python, and some interesting packages, one for R as well. Um, what kind of, so I'm curious about like, because I haven't heard of SnakeMate, for example, but is it like something similar to Dask, or is it a little bit more general?
No, I think it's closer to what Scott was describing with like Pegasus, kind of like a workflow management, like kind of task kind of organizer. So like in the sort of like aim of USGS doing a lot of like science that others could reproduce, it's a way that sort of like you can essentially say like run this whole workflow and it'll just automatically kind of rebuild everything. And if the benefit also is if like one file changes, it then only rebuilds the things like downstream from there that need to get updated. So it's sort of like that way, but it also can sort of like dynamically kind of like organize itself. So like if you have a list of watersheds and you want it to do some calculations for each of them, you can tell it to just like branch over those watersheds and like do the computations. And if that list of watersheds changes, it just like updates and rebuilds the new one. So yeah, it's a little more work to like set up code in that structure, but for a project where you are going to be rerunning a workflow multiple times and making some changes as you go and want it all kind of reproducible, it can definitely bring some benefits in that way. So I don't know if Pegasus is specific to a certain language, but like the SnakeMake and targets are kind of like language specific versions of that. So
Okay.
SnakeMake's a Python package, targets is an R package.
Yeah, that sounds interesting. I'll have to check those out. I haven't
Yeah.
actually worked much with Pegasus. But Scott, you have, right? Yeah.
Yeah, we've used Pegasus for job scheduling for 10 years. Been around a while.
Okay. So it's like analogous to like Slurm that the VAC uses, kind of in this that it schedules.
Well, no, it's Slurm is just scheduling the jobs. Pegasus sets up those file requirements. It says, hey, this task, this block job has these required input files, and it generates these output files. And basically, by chaining those requirements together, you can say, I'm going to run this thing, and I need to run these 4 jobs before this job can run. And you reflect that by saying all of the outputs from those 4 jobs. So this 5th job says, I'm waiting for those files, this, and that. As soon as all of those appear, I run.
Yeah.
God.
So it, and
So
you can stitch that in with Slurm or other job managing queue managing systems to like we use the NCAR or Yellowstone, Cheyenne, petacomplex, hundreds of nodes. And we'd throw these out there, and we'd have multiple climate scenarios and multiple weather scenarios, and human land use change scenarios, and we'd end up with this tree of jobs that would be hundreds and hundreds of jobs, and it would just work down the branches based on file dependencies. So it's kind of nice.
Yeah, that sounds nice because it's like, so essentially you're like chunking up your workflow into different components, and then it's smart. Pegasus smart enough.
It works good if you've got a lot of small jobs that are communicating with files. It's not really for doing a big in-core computation in parallel, which sounds like Dask is more about, I'm going to bust up my jobs by, I'm going to take this data and slice it by columns or slice it by rows, and use 8 threads to calculate a particular computation for one data set. It's a different problem we're solving.
And I think it sounds to me like targets and SnakeMake are like that, but it's like more kind of like internal to the code. So like you'll like run a function, and if you like change the function, it knows to then rerun like that part of the code. Like you can input output files, and it'll keep track of if a file is updated or changed, but it's maybe just a little more tightly integrated with like kind of the code itself.
Nice. This has been some really great conversations. It's been nice to hear everyone's experiences with parallelization.
Thanks, Noah, for organizing this.
Yeah, I think for the next, so I think, yeah, for our next seminar, this sounds like, I think with parallelization, it's definitely something, it's like there's a lot to learn and there's a lot to talk about. So my feeling is like it would be worth a follow-up, maybe from a different angle, but I feel like it's definitely not one of those topics where it's like a one and done kind of thing. So I'm curious, like, do people have suggestions or requests for a different component, maybe diving deeper into some of like any of the aspects of parallelization we've covered today, or anything like that, or just other ideas for a research computing seminar for different topics in the future related to this or otherwise.
It might be cool to learn a little more about parallelization for acquiring data, because that's kind of the problem I'm running into right now, where I want to get a ton of National Water Model retrospective data from the S3 bucket. And one gauge can take like 10 to 15 minutes to get. And I need over 1,000 gauges. So I've been dreading even attempting it.
There are some other that would be a good conversation because there certainly are some other aspects there where some service providers will throttle you and say, yeah, you could use multi-threading and come to my server with 100 requests to download a gauge, and we'll shut you down because you're sucking up all our bandwidth and costing us, broadband.
I could see Amazon doing that.
Well, yeah, so that's kind of thing. Yeah, sometimes it's data rates. They charge you by the amount per time that you want to transfer. So you got to be a little careful with setting up some of these things because if you say, "Great, I'm going to just gulp, a terabyte of data over the next half hour," it's like, yeah, and we'll charge you for it at a different rate than if you sip it. So it would be a conversation to have for sure.
Yeah.
Maybe we can find some information along that about how to basically do efficient and cost-effective data scraping.
Yeah,
Might
that
be
would be
interesting.
nice because I don't know any of the factors for that, any of the costs associated with it. So
That'd be something to do. We'll probably take us, no later than like a week from now, we'll come up with a thought for what the next week's,
Right.
in the week after that, what the plan would be. So if you have any thoughts, any more details on what you might want to hear about, or would you want to take point and find an article and present it to us? This is not a Pat Noah Scott show.
Yes, and on that point, I will say, I know we've kind of been leaning into tutorials kind of by default, but between the three of us on our team, we're trying to stay away from that. So like what I did
Yeah.
in the notebook today, like, I think the last time I did this, I spent a lot more time on a tutorial, but this I like whipped up in the last half hour before a meeting. And like, so I don't see this as like, or we're trying not to frame this as like, take on more work and give a seminar or tutorial to the group. It's really can be like,
Yeah.
hey, like this is like a problem I'm having, or this is what I'm struggling with in my code. And like, I don't know, like I found these articles, but I don't really know. They're kind of out of my scope. What do you guys think? Can you guys help me out?
Yeah, if
And
you're
you
taking
gotta
more than
frame
an
it.
hour to prepare for this, it's too long. We want
Yeah.
you to, if you in the course of your research, if you find an article or you find a topic that has some interesting, commentary out there, bring it to us,
Yeah.
and you might all find it interesting.
Yeah.
Not
There's
like
a
you
lot
come
of
in
times-
as the expert. Just say, look at this thing I found. It's cool. We should read it.
Right. Any of those things that you bookmark and be like, oh, this would be nice to read if I had the time. This is that time. You know what I mean?
There you go.
So that's just food for thought. We're gonna try to steer it that way. I know for my part, I've kind of lent towards the tutorials, but we're gonna try to in the future lean towards more of like an open seminar and more just like exchanging information and experiences. So
Sounds
with
good. We gotta
that,
run.
yeah. All right. That's our time. And enjoy the week. And I'll send you an email next week on the next topic. Of course, reach out to us if you have ideas or suggestions or want to lead. And yeah, see you guys in a couple weeks.
Sounds good. Thanks, Noah.
thanks, Noah.
All right. Goodbye. Stop.